So, finishing up with the Lewis structure from the previous video, when we ended up adding all the lone pairs to get up to the total of 32 total valence electrons, we noticed that we had all the atoms had formal charges. And what we want to do is have these share electrons so that we minimize the number of formal charges. And so what we're going to be able to do is take one of the lone pairs on the oxygen and bring it so that it's shared between the atom with the positive formal charge. All right, we're going to actually do that on two of the oxygens. So the way that we can represent that is with this little curly arrow. We're going to say a little bit more about these curly arrows in just a second. But what it indicates is that this lone pair is now going to be shared between this atom and this atom right here. All right, and when we do that, it's going to do two things. First of all, it's going to go from having a single bond between these two atoms to having double bonds. But the second thing that it's going to do is it's going to reduce the formal charges. All right, notice that if you calculate the formal charge around this oxygen, we now have 1, 2, 3, 4, 5, 6 dots that or electrons that it would own, and we need 6 electrons for it to be neutral. So these oxygens are now neutral, whereas before they had -1 formal charges. The sulfur before had a +2 charge on it, and now it would be neutral. So by comparison, by sharing the electrons on those oxygens, we now have a structure where we have minimized the total number of formal charges. All right, and so this would be the commonly accepted Lewis structure. All right, so when you're drawing the Lewis structures, try to make sure that when you're done that you don't have structures where you've got unnecessary amounts of formal charges. So one thing that this particular structure of sulfate indicates is a little bit of a deviation of a concept that's introduced in most sophomore chemistry classes, and that's the octet rule. All right, the octet rule, there's a couple ways that you can say it, but a common way of saying it is that atoms like to be surrounded by the same number of electrons as the closest noble gas, which for most atoms was 8 electrons, and that's where we get the octet rule from. But we also know that for hydrogen, the closest noble gas is helium, so it only likes to have 2. All right, so for example, this structure right here, you can see it's obeying the octet rule. Again, there should be a negative formal charge right next to that oxygen. But like for example, this carbon right here, if you look at the closest noble gas, it's fluorine. It should have the same number of valence electrons as that, which is 8. So if we count how many are surrounding it, we've got 2, 4, 6, 8 electrons surrounding it. It's satisfying the octet rule. But if you take a look at this structure right here, take a look at the sulfur. We have 2, 4, 6, 8, 10, 12 electrons that are surrounding that. So that seems to violate the octet rule. And the thing is, with a lot of molecules, that's just the way the bonding occurs. All right, and what's happening there is what's considering expanding the octet. All right, and so here's a couple of structures, and sulfur is a molecule that is notorious for this. So for example, sulfate, right, would have this Lewis structure. It has 12 valence electrons around that sulfur. This molecule right here is called DMSO, which stands for dimethyl sulfoxide, and you'll notice that it has 10 valence electrons. This molecule right here also contains sulfur. This is hydrogen sulfide, and it has only 8 valence electrons. So this one is actually satisfying the octet rule, all right, the way we've traditionally seen it in the past. All right. So how does this happen? So first of all, this can only happen with atoms that are at least in the 3rd period. All right. One simple way to remember it is it's only going to happen with atoms that are higher than silicon on the periodic table. All right. So why does it have to be higher than silicon? All right. Well, here's a simplified explanation for it. All right. If you take a look at the configuration for sulfur, all right, 1s2, 2s2, 2p6, 3s2, 3p4, and traditionally we would say, okay, well, it ends there, because at that point, okay, we would not have these right here because we would have already filled in enough electrons for sulfur. All right, but if we were to keep on going, let's just recall what would come next. We've got the 4s2 and the 3d10 levels. All right, so the thing is that when you have a valence level that has these d electrons, all right, what can sometimes happen is that the electrons that are in the s and the p orbitals can be essentially promoted to that d level, and that can help it. Those electrons in the d levels can participate in bonding. So again, this is a relatively simplified explanation. A more technical explanation gets into this thing called orbital hybridization, which we'll talk more about when we get to organic chemistry. But just keep in mind that whenever you have elements that are higher than silicon, they can use the available d orbital capacity to help accommodate some of the bonding. All right. So some of the common elements that are going to make use of these expanded octets are sulfur, phosphorus, chlorine, bromine, iodine, and a lot of the transition metals. All right. So for example, if we wanted to draw the Lewis structure for PCl5, all right, it would end up looking like this. And again, if you were in sophomore organic chemistry, or sorry, sophomore chemistry, and you looked at this, you'd say, well, that phosphorus is not obeying the octet rule, and that's because it's got that expanded octet. All right, phosphorus has those available 3d orbitals that it can put some electrons in and allow it, and those electrons can participate in the bonding with the chlorine. All right, chlorate is another example. This would be its structure. There should be a minus charge on that oxygen right there. And permanganate is another example. All right, so this would be an example of a transition metal. This would be with one of the halogens here. And a lot of the times you're going to see it with the halogens is when you've got a halogen and a bunch of extra oxygens. All right, so chlorate, perchlorate, you're going to have it with right, hypochlorite is another example. So one thing about drawing Lewis structures is that so far we've always tried our best to do a completely thorough job in drawing them. All right, and when I say do a thorough job, what that would indicate is you're always drawing, if there are any lone pairs, you're drawing the lone pairs in, and you're always drawing the formal charges. All right. So the thing about drawing Lewis structures is once you get well practiced with them, you can start to draw just the formal charge and just assume that the person looking at the structure would understand the number of lone pairs. So as an example, first of all, I'm going to start off with just the different ways that you might see hydroxide drawn as a formula. All right, you might see it OH minus, you might see HO minus. Sometimes you see it with parentheses around the atoms with the charge on the outside, but these all mean the same thing. Right? Notice in all of these, they don't bother drawing any lone pairs. All right. So if we did want to draw this as a Lewis structure, all right, we would want to show the bond between the oxygen and the hydrogen, and that's what I've shown here. All right. Notice that in this particular structure, we have shown all of the lone pairs. There's 1, 2, 3 lone pairs, and if you do the determination of the formal charge, you essentially break that bond apart. That would put 7 electrons around the oxygen. That means it would have a -1 charge. And that's why we have put that charge there. So this way of showing it puts in all the lone pairs and all the formal charges. So this is the most thorough way that you can represent a Lewis structure. However, people, by nature are always looking for shortcuts. And a lot of times when people are drawing Lewis structures for hydroxide, they'll just do this. All right, so you draw in the bond, you draw in the oxygen, but you just put the minus charge there. All right, and when someone does this, what they're doing is they're assuming that the person looking at it would understand how many lone pairs would be required to give that a minus charge. So what you need to do when looking at this is ask yourself, okay, if oxygen has a minus charge, how many total electrons would it have? So for neutral oxygen, it needs 6 to be neutral. So for it to be -1, it would have 7 total electrons around it. Well, it's going to have 1 electron after you break that bond. So what that would mean is that it's assumed that there are 3 lone pairs around this that just aren't drawn. All right. So once you start doing enough chemistry, you're going to find that people start to use these shortcuts more and more. All right, and it's just going to become a lot easier just to recognize the number of lone pairs that aren't shown. All right, just want to point this out. In general, you would never show a Lewis structure where you show the lone pairs, but you do not show the a formal charge. All right. If there is a formal charge as a result of the number of lone pairs that are around the atom, you would be obliged to show that charge. All right. One other way that you might see things, and this is fairly uncommon, but I have seen it before, is something like this. All right, where if you wanted to say, well, one of the electron pairs is going to end up being involved in some bonding at some point. All right, we're going to get into reaction mechanisms. You might show the molecule like this, just to indicate the lone pair that is going to be involved in some action. All right, so the negative charge would indicate that it's hydroxide, and in this case you would assume that there's 2 lone pairs that just aren't shown here. All right, so just as practice for this, what I've done here is I've shown a couple of different Lewis structures with some have formal charges, some don't. And what I want you to do is think about, like, if any of these have any lone pairs that are assumed to be there but just aren't drawn. All right, so pause the video, take a look at the structures and see if you can figure out where the missing lone pairs are. All right, and just a hint, some of these might not have any missing lone pairs. Okay, so in the first one, you should have realized that with that being a positive charge there would be no necessary lone pairs around that nitrogen for it to have a positive charge. So there would be 0 assumed lone pairs. So this structure, even if we do it as thorough as possible, would it look exactly like this. Okay. For sulfur to be negative, it would need to have 7 valence electrons. That means we need to have 3 lone pairs. All right. So this structure actually means this right here. All right. pH3. All right. Notice there's no formal charges, which would indicate that it's completely neutral. So in order for this to be completely neutral, all right, that phosphorus needs to have 5 electrons around it. All right, so for it to have 5 electrons around it, you would have to have a structure like this. So what that means is that there's 1 additional lone pair that's on that phosphorus that's just not shown when you draw it like this. Okay, and so just because they don't show the lone pair, remember, they might just be assuming that you realize that it's there. Right? In this particular structure, for that oxygen to have a positive charge would mean it would have to have 5 electrons around it. So if you count it up, 1, 2, 1 from each of these bonds, 1 from this bond right here, that's 3. So there's got to be 2 more electrons. So there's a lone pair right there. And one quick way to check it is to see what the formal charge should be if you draw it this way, and you'd realize that there's a +1 formal charge. All right. Last example, and this is kind of a harder one right here, but this is something that, especially if you go on and do organic chemistry in college, you'll see things like this, where I've drawn a minus charge on this carbon. All right, and notice I've drawn this as a line angle structure. The way to do this, what this would indicate, first of all, if that lone pair was not there, or sorry, if that negative charge wasn't there, you would assume that there's 2 hydrogens there, so each with a single bond. All right, so what this would indicate is actually this right here, all right, where this carbon right here has 3 bonds, all right, 1 to this carbon, 1 to this carbon, 1 to this hydrogen, and instead of having another single bond to a hydrogen, both those electrons would be owned by that carbon. So if you calculate the formal charge on that carbon right there, you would have 1, 2, 3, and then 4, 5 from the lone pair. That is 1 more electron than what it needs to be neutral, and that's why it would have that minus charge. All right. All right. So I do want to point out that the most common atoms that you're going to see the assumed electrons are sulfur, nitrogen, phosphorus, and oxygen.